I'll be talking about Nelkin scaling in turbulence, a word which is, liked very much by Uriel, turbulence, Burger's equation and turbulence, something like that. And well, I met Uriel like 3 years ago. Well, my passport would suggest on 24th of November 2008, and so I'm a little late in my interaction with Uriel, but that was early enough in my career. So according to him, because my hometown was near Himalayas, so I've been Himalayan Yeti who has to be taught how to optimize things and speak properly and communicate properly in scientific matters. So now you will be the judge whether I have been able to communicate properly in this talk. So in this talk I'll basically summarize whatever I have worked with Uriel. I'll give a little bit introduction about the ESS work which we had done a year ago, and then I went on to talk about something Nelkin scaling. Much of the talk probably has already been introduced to you in some of the other talk given by Uriel or some other collaborators, Walter Pauls and Shamriddhi. But still I'll go through it. So, well, this is kind of very outrageous thing to show to this community, but still to get notations clear. So, in Navier-Stokes equation, we know how we define the longitudinal velocity increments, which is you take the velocity difference at 2 points in 3D turbulence and then you project it on the separation. Now if you raise it to the power p and you do ensemble average of the longitudinal velocity increment, these are what are known as structure functions, longitudinal structure functions, and they are known to scale as separation raised to the power zeta p at very high Reynolds number. Over inertial range, you know this zeta p shows a multifractal structure. In 1990, Nelkin studied velocity gradients moments, or rather grad moments, or moments of velocity gradients, and he was more interested in showing that within the paradigm of multifractality, you can connect the grad moments. Grad moments are the derivatives taken of velocity and raised to the power p, and then you ensemble average. It's supposed to scale as Reynolds number raised to the power some chi p, where chi p will be defined as Nelkin exponent. Now, this Nelkin scaling, Nelkin studied with a view to connecting the grad moments scaling exponents or the Nelkin's exponents. He didn't name it after himself. So, Nelkin exponents, and he tried to connect it with the scaling exponents of higher order derivatives, scaling. Now this Nelkin scaling can actually be connected with multifractal structure function exponents zeta p's, which you can find in Uriel's book. Now very recently in 2007, Schumacher, Yahot and Srinivasan, they found out that using very high resolved 3D direct numerical simulation, you can see that Nelkin scalings are present. And they are not only present at very moderate Reynolds number of around 200, they are present very, prominently, but the nice thing is they are present at such low Reynolds number that where you don't see any scaling of structure functions. So we wanted to find out how this works, or things like that. But I'll talk in a chronological fashion. How we stumbled upon the problem and how we did it. So before that, what we had actually started working with was the ESS and trying to explain extended self-similarity within the Burgers equation model. Just to remind you, ESS extended self-similarity is if you plot velocities, third order velocity structure function with respect to the separation in log-log plot, and you plot the sixth order velocity structure function with respect to separation log-log plot, you see certain scaling regime, which can be extended if you plot sixth order velocity structure function with respect to the third order velocity structure function in both infrared and ultraviolet regime, by which I mean the large separation and small separation regime. This is what Benji et al. Had found out in 95. There weren't, very fundamental explanation of how ESS works. It's not quite, you of course know it's not quite trivial to find out explanation right from the Navier-Stokes equation. But so we thought, well, maybe Burgers' model can help us to understand how ESS works. Now, the thing was, in 1995, Benzi et al. Had already said that Burgers does not work, ESS does not work for Burgers' equation. This is the Burgers equation, where you have the time derivative of velocity and this advection term, and this is the usual viscosity term. We are taking a very simple case, so it's unforced, and we will start with a very simple initial condition like sin x or something like that. And we know that if an initial condition is allowed to evolve according to the Burgers equation, it will develop shocks, and then you can find out the structure function in Burgers equation, and the zeta p's show this kind of structure, where you have zeta p to be 1 for all p, for all integral p from 1 upwards. So what we found out was this. So we found out if you increase the resolution more and more and more, if you go on from a resolution from Reynolds number, where Reynolds number for the Burgers case has been simply defined as the inverse of viscosity. If you increase the Reynolds number from 100 to 200, 10 cube and 10 to the power 4, you see there is a slight, the inertial range scaling is showing up. So what I have plotted is separation, h, versus the sixth order structure function, which has been compensated by h, so you get a flat looking plot.
Which one is which?
Yeah, so the solid line is the ordinary plot. I have not yet used the ESS. Now, once the ESS has been used properly, where by properly I mean we use a proper deputy for the separation, which is S tilde 3, where S tilde 3 is defined as the third order structure function, where we compensate it by minus 12 epsilon, where epsilon is the rate of dissipation of energy. We use this particularly because we know that there is an exact analogous scaling law for S3 in Burgers equation, which is S3 is minus 12 epsilon L, where L is the separation, or H in this case. So you can really use this as a deputy of H. Now these dashed lines are the ESS plots, where now we have plotted structure function of order 6 with, and compensated structure function of order 3, it's the proper deputy. Then we find the ESS. Well, here if we concentrate in here, it doesn't make much of a difference because we don't have inertial range to start with. But as the Reynolds number increases more and more, we can see the ESS type plotting is increasing the scaling regime. Well, not the scaling regime, it's increasing the way the scaling looks to be increased in the ultraviolet regime and in the IR regime, in the infrared regime. And the explanation we gave in the paper was, the dominant scaling, which goes as H, comes from the separations which straddle the shock. In the infrared regime, there is a deviation from the leading scaling. And from the and what happens in infrared scaling is that there are corrections which come from the separation, which are straddling the shock, but are just well, they're straddling the shock, but they are such that they have to invoke the velocity just on the left of the shock and just on the right of the shock, where you expand the velocity by Taylor expansion, and so there will be subdominant corrections coming from infrared regime because of such separations, and they will cause the deviation. In the ultraviolet regime, it's because of the finite viscosity that the shock width increases, and the separations which lie within the shock width, they have to obey the usual tangent structure of the shock, the tan hyperbolic structure of the shock, and when one uses that profile, one finds out that in the ultraviolet regime also there will be an extension. Now, where from the extension comes is due to the fact that the subdominant correction to the leading order exponent is getting weaker when we use ESS type plotting. So that's all about it. Now the next question that was asked was, can this whole explanation be worked for the case of Nelkin scaling? Now, for Nelkin scaling, as I told you, it was found that it appears at very low Reynolds number, or rather at moderate Reynolds number, when the structure function scaling has not shown up. And then we also found out that really it works even for Burger's equation, and one can actually find out that ESS works, and ESS type plotting works also for this Nelkin scaling. Now we again started with grad moments, which have been defined for the Burger's case in this fashion, where you take the derivative of velocity with respect to x, and then you raise it to the power p. You take a periodic box, so you normalize it properly over 2 pi. Okay. And there also exists exact relation connecting viscosity, second order grad moment, and energy dissipation, rate of energy dissipation. And so it seems that we can probably use M2 as one of the deputy for Reynolds number, because nu is 1 over r, so you can write M2 as epsilon. You can write r as M2 over epsilon, so maybe that can be worked. Whatever be the case, the idea is to check out whether the grad moments, which is supposed to, we conjecture that it has an algebraic expansion like this, where you have this leading order exponent, which we call chi p, and then you have subleading corrections, which will account for any deviation which we might see. The leading order exponent can actually be understood heuristically quite simply. So this picture has been exaggerated. So you have a shock which has a shock width of which goes as the order nu. Now, a velocity gradient will, since this distance is the order nu, so the velocity gradient will go as order 1 over nu, which will mean the velocity gradient will go as order r, and so the pth power of velocity gradient will go as order r to the power p, and then the shocks cover a fraction of distance, which is like order nu. So when we average the velocity gradient raised to the power p over the periodic box, then we find out that for the Burger's equation, the leading order exponent or the Nelkin exponent should come out as e minus 1. Fine. So then we simulated and we tried to find out Nelkin scaling in the Burger's equation by doing pseudospectral method. And now what we find here is this blue points are the usual plotting. By usual plotting, I mean we are plotting compensated grad moments. So we have compensated it with r t minus 1, the leading order exponent, so that it appears flat with r. And then we see that we really see Nelkin scaling, and this scaling deteriorates as you increase the order P, which is obvious. The thing is, this appears at very low Reynolds number. I mean, at this low Reynolds number, you see at Reynolds number 100 or even lower for the lower order P, we do not see any scaling in the ESS in the usual structure function plot. So it matches with what Schumacher et al. Had to say. Now we tried ESS type plotting, where we substituted R by deputy M2 over epsilon, where M2 is the second grad moment and epsilon is the rate of dissipation. You find the red lines show the increment in the scaling range. So we see it looks obscenely straight, but there is a slight bend upwards. So we are seeing that even in Burgers equation, Nelkin scaling works, and we can combine it with an ESS type plot, which can increase it even further. Now, we thought the theory would be just the way we could explain ESS for structure functions, and we can do it all. Now, we know that we can use Hofkohl transformation on the Burgers equation to change the Burgers equation to a well-known diffusion equation, and then we can find out solution for the diffusion equation using green function technique, things like that. And then we can use the method of Stevens descent for large enough Reynolds number to show that the grad moment for Burgers equation will follow algebraic expansion, which goes back to the power p, the subdominant correction with p minus 1 and p minus 3 and so on. Now, well, one should have done this theoretically, but it turned out too complicated for me, and we then thought that there is a nicer idea to apply, which will give us much more insight and something new which we want to comment upon. That we want to use a method called asymptotic extrapolation. Now the next slide I'll just flash, but now I'll try to explain what we have done here. Now, what exactly is meant by asymptotic extrapolation is that suppose you want to read off scaling from this plot. What is the scaling exponent? One way would be to use ESS, extend the scaling range, then you can fit it with using the least square technique, and you find out what the exponent is. Well, as it turns out, probably this may not be the most accurate and precise way of calculating exponents. And also, you probably are not going to get any handle on how the subdominant terms are looking like. So there is a recent technique proposed by Joris van der Hoeven and extended further and worked upon it by Waterpass and Frisch, where one does something like this. Suppose you have a function, and you want to find out what the functional, and the function has an asymptotic expansion. And you want to find out the leading order, subleading order, and the sub-subleading order of all terms of that asymptotic expansion. So how would you do that? It turns out what you can do is that you try to find out, first of all, you define the function on a regularly spaced grid, where you take the grid points as high as you can, and then you define at every grid point, you find out, or rather calculate at every grid point, value of the function as precisely as you can. And we did it with a precision of 400 digit. Well, this is not, well, okay. And then what you do when you have that, grid line with all the points having the value of the data, value of the function on the grid points with high precision, you start applying some transformations, some very simple arithmetic transformations, like you take differences, different successive data points, or you take inverse, you take second ratio, things like that. And what happens is, in the process, if you take the sequence of transformations cleverly enough by some trial and error, you end up finding that you will get some stages where the data points asymptotically goes to some flat regime or some constant regime. And once you go there, you can turn the crank back, you can invert the transformation, and you can find out how exactly the leading order exponent is looking like. Then you can strip off the leading order term from the function, then you try to find out for the subdominant corrections, and in this way you can really find out all the exponents and constants in the function. So we used that technique and we could find out values for chi p and the subleading order correction and sub-subleading order correction and all the coefficients, and you can see the accuracy is not bad. Here we have truncated the values where our method agreed for Reynolds number up to So here we truncated the data when we found out that our 200-digit precision data agrees with our 200-digit precision data. So that's it. So what I want to say is we can use that technique very accurately and we can find out how Nelkin exponent works and things like that. And we can also find the subleading order corrections. Now how that the ESS type extension in Nelkin scaling works? Well, it's again all about subdominant terms and how you find it. You then see the grad moments have this leading order exponent and the subleading order. Leading order term and subleading order term. When you choose proper deputy, you find out that the leading order term remains almost exactly the same. The subleading order term gets changed, where b tilde p is now related to the coefficient of subleading term of grad moment in this fashion. The point is now if you want to find out the critical Reynolds number, or not the critical Reynolds number, rather threshold, the threshold Reynolds number over which the subdominant terms will become weak enough so that they cannot show up and you can see Nelkin scaling properly. That Reynolds number, this is for the non-ESS type plot and this is for the ESS type plot. So that kind of, that threshold Reynolds number decreases. That is related to the diminishing of subdominant correction terms. So this thing, so we can see the Nelkin scaling not only works, the ESS type plot can explain, can be explained in terms of subdominant corrections getting weaker and weaker. Now, we wanted to make contact with the way Navier-Stokes simulations are done, and so we wanted to do it, do the simulation of Burgers equation in pseudospectral method. So what I have plotted here. Okay, so as you will remember that we have calculated the leading order Nelkin exponent and using the asymptotic extrapolation method to quite some accuracy. Now we do this pseudospectral simulation of Burgers equation and we use asymptotic extrapolation method to find out Nelkin exponents for 6th grad moment and 4th grad moment. And we know the theoretical value, which is just p minus 1. For 6 it will be 5, for 4 it will be 3. And then using the theoretical value and the value we find out from pseudospectral simulation, we calculate the relative error in determination of Nelkin scaling. We do it in two different ways, or rather in two different sets. In one set we use double precision data, in the other set we use quadruple precision data. And what we find is interesting, that the amount of relative error you obtain with quadruple precision data at around Reynolds number 52 is not even achieved when you use double precision data and you go up to Reynolds number 1000. So
you didn't give the number 1000.
Okay, I said 1000. I should have said 1000. So 1000. Sorry, 1000. And then, this is a kind of punch line of our recent work, where we feel that at least within the paradigm of Burgers equation, if you want to determine different scaling exponents, or maybe even the coefficients, increasing resolution is not the right strategy. Probably one should increase the precision. Now, I'll conclude it here, almost on time. So, I will summarize what I have talked until now. That we found out ESS does work for Burgers equation, and it's all because of the diminution of intensity of subdominant corrections. Even the Nelkin scaling can be found in Burgers equation, and it can be even improved by using some ESS type plot, which we have adopted on the usual ESS technique used by Benji et al. It will be interesting to check, whether this ESS type plot for Nelkin scaling works for 3-dimensional Navier-Stokes equation. And well, as I said in the last slide, in the Burgers case at least, we think it's more efficient to increase the precision in order to calculate the exponents rather than increasing the Reynolds number. Well, and of course, it remains to be seen whether this result of precision versus resolution trade-off goes to other multidimensional problems or not. It's a nice starting point, I would say. Yeah. So with it, I would like to thank you.
Yeah. Can we see the punchline slide? This one. So it seems that I was wondering, these look like systematic errors. I mean, not random errors. They look very nice.
Yeah.
So it seems that by working in double precision rather than quadruple precision, you make some larger amount of systematic error, not random. Huh? So I was just wondering, what kind of average do you have in this flow? I mean, how many shocks do you have, etc.?
Oh, so this is just this simulation has been done just in a periodic box.
Yes.
So you take the initial condition to be the sine wave, and then you have the shock in the periodic box, and then you.
So it's just one shock.
No, I mean it's a shock with the periodic box and you.
solution.
The deterministic, the one with the sine
Yes,
X
yes,
initial.
simple
Okay.
thing. We went to the simplest case.
Okay, so that's kind of surprising.
Yeah. But let me also mention, I mean, this relative error also depends, it kind of depends on the data processing technique that we have used. Because in the asymptotic extrapolation technique, you need to have very high precision data, because you need to do transformations on the data, and if you don't have enough precision, then the rounding noise will come in due to those transformations, and that can also contribute to the error.
But then you have several steps.
You mean
Yes.
Hopf-Kohl or do you mean Semperman? Do
Hopf-Kohl?
you use the Hopf-Kohl transformation?
No.
Okay.
Okay. So I'll just come here. I sabotaged a few slides from Julia's talk. So what we mean is, suppose you have a function like this, okay, and you want to determine all the coefficients and the exponents from here. Then, once you have defined the function over equally spaced grid points, you do transformations which are inverse ratio, second ratio difference, something like this, which is 1 over gn. So you are doing transformation on the data point, on the grid, and then you see if you apply second ratio, then this it seems to attain an asymptotic value at larger enough grid point. And so if you keep on doing these transformations, you have to do some trial and error, of course. You will reach a very flat stage at some point, and then you can turn back, undoing the transformations, and you can find out from here you can find out what the function looks like. So you may have to go through various transformations, analyze the data. But as you can see, as you are increasing the number of steps, here you see this is an asymptotic flat regime which came from here. It looks quite good. But here at the 6th stage of the transformation, this is also an asymptotic regime, but it's not as good as this. So it's because there's lack of asymptoticity and there's rounding noise coming in. So these are also going to contribute. So these are the transformation I was talking about.
But are you saying, is the gist of your story that we should compute at low Reynolds number because they have the answer?
If
With
you
high
want,
precision?
for buggers, yes. For others, maybe you can decide.
Yeah, I just want to say a word of caution, because of course, when you do it Burgers equation, you don't have the problem of n isotropy. It's one-dimensional problem finished. Usually, it's then isotropy that is defeated. That is to say that when you're at a low Reynolds number, you still didn't get away contribution from various sectors of the symmetry group, and then the bad thing is you don't have scaling laws, nevertheless you don't have good scaling laws in a similar way for the various structure functions. When you plot one as a function of the other, you seem to get a scaling law with a wrong number. So ESS can be a very good method to get a parent scaling law with the wrong number, which you don't have here. So this accurate precision here.
ESS is a way of depleting subdominant contribution and therefore putting more emphasis on the dominant one. Asymptotic extrapolation does the same thing in a much subtler way, and it is a bit harder to implement, but you get a lot more truth out of it. But whenever you have subdominant contribution, whether they come from anisotropy or from something else, it's a good way to
pull out
simultaneously dominant and subdominant, but it's expensive because you have to repeat the computation. I mean, moderate Reynolds number, yes, but you have to do it for Reynolds number, a large choices of Reynolds number, say from 20 to 200 or so. You may have to use 700 data points. So all these calculations are very rapid, but you need many of them.
Yeah, but you were saying that the scaling is visible at low Reynolds number, that is to say in the
Yeah,
dissipation.
well, you wouldn't, if you stupidly plot your data, you wouldn't see a good scaling. You have to use a symptotic extrapolation to get rid of all this mixture of dominant.
Right, but the question is physics, not mathematics, which is the flow at low Reynolds number, you say, has already a scale.
That's voodoo.
No, this is what...
But the thing is when you plot...
It's voodoo, I mean, because the physics just is not there. No matter how you manage all the terms, it's just not there. It's a low Reynolds number flow, it does not have a cascade.
That's the question.
No.
It has a shock in burgers, which you can try to, but because
Grisha, this kind of confusion arises only if somebody uses the word low Reynolds number instead of moderate Reynolds number. Then, of course, one gives the wrong signal. We're talking about Reynolds number from a few hundred to 1,000.
Lambda. Lambda.
no.
Which
No,
the global.
Lambda, of course not. Yeah.
You have very little scale.
And did you see Schumacher's result?
No, I mean, voodoo is kind of very impressive. I mean, these results, I mean, people, raise and go, and I mean, and many people seen it, but there must be some qualitative explanation. I mean, in a sense that why it's such, they're like...
It's not voodoo, it is just that it is a much better idea to look at the dependence on Reynolds numbers of moments than to look at structure functions.
That's not all.
It's just that.
This is definitely better at any Reynolds number.
Yeah.
Yeah, I'm sorry. I took. Okay, let's move to the next.